Okay, so in this talk, we're not going to look broadly at applications. We're looking specific at UQ tools. Specifically, we're going to look at surrogate models. So surrogate models or meta models are simple data-driven approximations of the input-output relationship of a complex numerical model. For this talk, we're going to specifically focus on iterative adaptive development of meta models to support specific uncertain quantifications, UQ task. So in other words, we're not trying to establish a global accurate characterization of the input-output relationship of interest. Rather, we're trying to do it. We're trying to do good enough in order to perform the UQ task at hand. So we'll try to convey all these theoretical developments within the context of two specific applications, and the main one I'm going to focus is design under uncertainty. Towards the end of the presentation, we'll talk a little bit about stochastic sampling. So let's try to motivate the use of meta models from the perspective of design under uncertainty. So this is my problem. I have a model which can be, for example, a car driving in a rough road, a wind turbine under wind or sea excitation, or a structure under earthquake excitation. So for this model, I have for this system, I have a numerical model, and which includes some design parameters I'm going to call by X. Sort of these are the controllable system parameters I'm trying to optimize, and some uncertain model parameters, which I'm going to denote by theta. And since they're uncertain, these are sort of my random variables, I'm going to assign a probability distribution function to them. So evaluation of the system model provides the response, and then the performance evaluation model pretty much comes and defines our performance measure. It quantifies the favorability of this response. I'm going to denote my performance measure as age, and you can view this as a function of the response as the age of z, or as a function of your design variables and your model parameters. And you see here that I do formally a distinction between what my response vector is and what my performance measure is. This is very common for many engineering applications, and always I'm going to assume that z comes from a computationally complex model, whereas age comes from a simple analytical function. For example, if you're looking at a wind turbine, your response could be the stresses of the different components that you can derive through a complex finite element model of the turbine, and your performance measure, for example, if you're looking at the reliability of the system, is just an indicator function which you can very easily calculate as soon as you know what the response. In order to make our lives a little bit more challenging, we're going to assume that the model that provides this response, it's a black box. So it's a complex numerical simulator, and that you don't have access to. In other words, you can evaluate the response, but you cannot get other information such as gradients. So this is the setting of our problem, and this gives birth to what we call design under uncertainty, where we try to select our design variables in order to minimize our performance objective, which is simply the expected value of our performance measure over our uncertain parameter. So this is just an expectation operator. It corresponds to a high-dimensional integral, the expected value of h under P of theta. Now, this for single objective optimization. For multi-objective optimization, ultimately you have multiple objectives. I'm going to use the subscript I to distinguish between the different performance measures of the different performance objectives. And if these performance objectives are competing, in no reality, you don't have a single solutions, but you have the Pareto set of dominant solutions. Generally, we like to visualize it in the objective function space. Pareto front looks something like this, and the dominant designs pretty much corresponds to designs within the feasible objective space that you have no other design that simultaneously can improve upon all the objectives. So pretty much it is the front that's at the left part of the physical objective space. So this is sort of the block diagram representation of the previous problem, and in order to solve this optimization and identify the Pareto set, we need to come and evaluate the objective function, which corresponds to a high-dimensional probabilistic integral, with dimension as high as the number of uncertain parameters that you have. And since we have assumed that we're going to have black box numerical model, and you can also have complex probability distribution as well for theta. The only generalized approach that you can do these evaluations is through stochastic simulation. So this is, Monte Carlo simulation with, important sampling, and pretty much you can come and substitute this sample-based approximation of your objective function and try to solve the optimization problem. So this gives birth to what, to a simulation-based optimization, where the simulation component comes from the fact that you evaluate your objectives using stochastic simulation. This is a very powerful approach, very generalizable approach. We have put no constraints on other probability distribution, the numerical models that we can employ. It can be any black box, a function that corresponds to the problem that you're interested in. But the challenge are in the computational efficiency when you try to solve this optimization problem. Because you have an unavoidable estimation error coming from the stochastic simulation, also you have a significant computational cost because a single evaluation of the objective function requires n evaluations of your complex numerical model, and also since we adopted, we said that we can also accommodate a black box numerical simulators, and in order to get great information, numerical differentiation might be the only possibility. Of course, there are some remedies to address these challenges. For example, you can use importance sampling on common random numbers to reduce either the absolute or the relative importance of the stochastic simulation error. You can, if you have access to supercomputers, you can use parallel computing to reduce the computational cost. Pretty much because you have independent evaluations here. This is what we call embarrassingly easy to parallelize problem. Or you can come and rely on gradient-free approaches or algorithms appropriate for complex global optimization. And all these are very good tools, and they give remedy to a lot of the problems that we have in this simulation-based design under uncertainty problem that we try to solve. But in the context of this presentation, I'm going to focus on something completely different. So I'm going to focus on how surrogate models can help us solve this problem. So for those of you that are not familiar with surrogate models, let's give a very brief overview. So as we already talked about, surrogate models are data-driven mathematical approximations for the input-output relationship of a complex numerical model. It's something many times we call this as a processor computer code. So Y is going to be my input, Z is going to be my output. And they're formulated based on a database of simulations. We typically call them experiments, or many times training or support points that you obtain using your complex numerical code. And based on this information, then you establish the surrogate model approximation. Of course, there are many types of surrogate models, neural networks, response surfaces, but specifically for uncertainty quantification applications, what's getting a lot of traction, and we're going to discuss why is the Gaussian process metamodels. Generally I'm going to refer to them as JPM. So, Gaussian processes pretty much they approximate the function as a realization of a Gaussian stochastic process. So in other words, you don't obtain a single meta model, but you're obtaining a family of meta models that have some predictive mean and some predictive variance. And you calculate this predictive mean and predictive variance based on the database of experiments that you have. So these are a little bit of the numerical details. We don't care that much, but ultimately what I want to focus a lot, so these are sort of the estimates of the predictive mean. It pretty much relies on simple matrix manipulation. So after you train your meta model, being able to make predictions, because again, these are simple matrix manipulations that you can very easily vectorize, requires negligible computational burden. And apart from the predictive mean, you can also get an estimate for what the predictive variance is of your meta model. Again, straightforward, a matrix manipulation. So from a computational perspective, very efficient to make predictions. So there are actually, there are many interpretations that you're going to see for Gaussian processes. You can sort of view them from the Bayesian predictive as a set of predictive model, or coming in a little bit of the more deterministic perspective as a surrogate model that gives you some mean predictions, but also comes and quantifies what is the local error associated with these predictions. So I'm going to, pretty much they're equivalent, interpretations, and in these presentations I'm going to be relying on both of them. So let's come and do a one-dimensional graphical demonstration of how JPMs work. So this is sort of your exact function. Remember, you're going to do some experiments. You're going to evaluate that exact function in a number of points. So this is all the information that eventually you have. You're going to train your metamodel, which for Gaussian processes corresponds to optimization of what is the hyperparameters for the correlation function of the Gaussian process. And once you select those hyperparameters and you train your metamodel, very quickly you can get the predictions, what is your predictive mean. But on top of that, recall that you can estimate the predictive variance. So you can see that the predictive variance is exactly 0 at the points where you have experiments. Gaussian processes are exact interpolator, but in between the experiments, you can have a significant error. So in other words, coming and exploiting the full probabilistic nature of your metamodel, you not just have a predictive mean, but you have a family of models here. I'm sort of plotting the mean plus or minus 1 standard deviation. So if you want, you can completely forget that you have the estimation error information. You can just use the blue line, the predictive mean, or you can come and use the error estimates. And in this case, sort of you can get conditional realization of what your predictions are. So all these guys here, it's pretty much you sample from this Gaussian distribution, so you're incorporating beyond what are the mean prediction is the information that you have about how good of a job that you are doing. And of course, the accuracy of Gaussian processes relies a lot on the experiments that you have. Yeah, the optimization of the hyperparameters is important, but what is more important is the correct placement of the experiment. So you can see here I had 5 experiments, and if let's say I add 3 more, I have significantly better predictions. You can see how closer the blue curve is in the green, and how your predictive variance reduces simply going from 5 experiments to 3 experiments. So then let's spend a few minutes figuring out how you select these experiments, what we formally call a design of experiment. So this is the information that you have. In reality, you really don't know what the exact response is, but you have the predictive mean, but also you have the predictive variance. So if someone was asking you where you should put experiments in order to have the greatest utility, evidently you shouldn't put it in regions where you think that your metamodel thinks that is good, already doing a good enough job. So it's putting in areas where the predictive variance that you're estimating is high. In reality, since you don't care that much about your response, but in your performance, you can propagate that uncertainty from the response from Z to H using like a first order Taylor series approximation. Ultimately, this is your utility metric. It comes sort of and tells you what is really the value of information that you're going to obtain from each experiment. And on top of that, remember that you not try to get global accuracy for your surrogate model. Our goal was to perform with sufficient accuracy a UQ task. So beyond this utility metric, you also have a preference function. It pretty much tells you within the whole input domain what are the specific subdomains that are of greater interest for your UQ task. For example, if you were looking at simple estimation of an integral, this would be sort of your importance sampling, like a function like the integrand of your integral. So in areas where this preference function has lower values, you shouldn't put more experiments, because improving the accuracy there at the end of the day has a small impact on your overall UQ task. So you can design of experiments, having in mind what is your preference function, is what's your utility metric. And in general, this is a very challenging problem, like to actually calculate what is the next optimal experiment requires a significant computational effort. But we can try and solve a suboptimal problem, and which in this suboptimal solution, if you would do a sample-based approach, we're going to see that it comes at a significant smaller computational cost rather than coming and calculate the actual best next new experiment. So let's talk a little bit about sample-based design of experiments. So we're going to start by simulating a large numbers based on preference functions. So these are samples where, based on our UQ task, we know that information is going to do a lot of good. But of course, some of the samples correspond to regions where your meta model already has good enough accuracy. So in other words, you don't care about them. So you go to utility metric and you remove some of the samples based on what is the utility metric value. And now these are samples that, we like based on our preference function. Also, we already know that we're not doing a good job, so they're good candidates. But if you go and use all this as the next experiment, you don't need all of them. Because some of them, the ones that are close to one another, one gives you good enough information for the other as well. So rather than including all these as new experiments, then you can cluster them into the desired number of experiments so that you avoid close proximity experiments. And so this is, these three stages gives you at the end your design of experiments. So you're getting like these final three experiments that are populated in regions where are going to be beneficial for your UQ task, where your meta model is not yet accurate enough, and also you're avoiding addition of close proximity experiments. So with these three, now you can add them, you can evaluate, you can adaptively, by adaptively I mean that we selected the new experiments with information already from the meta model that we had with the initial 5 experiments. We can add these 3 experiments, and you see that you get significant big improvement of your accuracy. So from now on, whenever we're trying to get new experiments within our implementation, I'm going back into this sample based design of experiments. So in summary, we're gonna we like JPMs for uncertainty codification for a number of reasons. They're computationally exceptionally efficient. So once you have your database and you train your a Gaussian process meta model, you can do 100,000 of predictions with very small computational cost. They have been proven very accurate for approximating even complex functions, and you can leverage them to very easily get graded information. And finally, they have this local estimate for the predictive variance, which especially can be very, very useful for an adaptive design of experiments. So this is our meta model. Now let's come and see how we're going to incorporate it into our design or under uncertainty problem. So this was where we had stopped. Another question is, okay, what should be our input? What should be our output for the meta model? For example, you can select as input the design variables, and as output your performance objective. This is sort of what the efficient global optimization is trying to do. But we can try something different. So what we're going to adopt here is development on the meta model of what we call the augmented input space. So our Y is composed of both my design variables and my uncertain model parameters. In other words, with a single meta model, we try to address both the calculation of the expectation, so the uncertainty propagation, and also the identification of the Pareto front, the design optimization. And with respect to output, we're going to target what is the computationally intensive part of our initial process, which is pretty much as output having the response of our computationally expensive black box simulator. And then pretty much for calculating the performance evaluation, we're going to explicitly incorporate now the meta model error. So this is sort of our modified performance measure, which is a function not only of what the predictive mean, but also what is the predictive variance. I'm going to give one example later in our application, but for estimating now the modified performance, we explicitly come and incorporate all the information that we have from the family of metamodels, not just the predictive mean, but also the predictive variance. So how this thing works, so we get some training points that cover variation of both x and theta. We evaluate based on our computer simulation their response. Based on that, we come and we train our meta model, and then we solve the optimization using the meta model based approximation. So in other words, we come and modify our performance measure to also explicitly incorporate the uncertainty coming from our meta model. So for any new design configuration that we are interested in the design domain, so pretty much using the meta model, we come and evaluate the response, the modified performance measure, and then we come and approximate our objective function or its gradient, especially since now we have gradient information coming from the meta model using stochastic simulation. And each single time that your design solution that you're trying to investigate changes, so you come and solve you come and identify the Pareto front using this JPM approximation. And the trick here is that whenever you try to investigate for a different design configuration, you still rely on exactly the same meta model, because you developed that meta model looking at variations for both x and theta. So in other words, you're using a single surrogate model to simultaneously calculate the probabilistic integral, so for the uncertainty propagations, but also explore the different design solutions for what we call the design optimization. This is what gives the significant computational efficiency, is the fact that our meta models have really simultaneously dual role. Now that we know how exactly we're gonna, calculate the objective function using our meta model approach, a little bit on the optimizer, how we're really gonna come and identify the Pareto front. Especially since we have gradient information, we're gonna rely on the epsilon constraint approach. So for the epsilon constraint, you start, so this is sort of your how in the design domain your contours of your two performance objectives look like. With epsilon constraint, you start by looking at each of your objectives individually, so sort of you solve the single objective optimization problem. So you come and identify through this single objective optimization the anchor points of your Pareto front, and then you come and convert one of your objectives as a constraint, and you optimize for the other one. So you convert your multi-objective optimization problem to two single objective optimization problems, and then a series of constrained single objective optimization problems. So sort of, you put a constraint, so in other words, you mean that you are optimizing in the interior of these contours, which are going to give you the next point in your Pareto front, and then you repeat this, and then you can get the Pareto set in the design domain, and of course the Pareto front in the objective space. So we're going to be relying a lot on epsilon constraint in order to solve this multi-objective optimization. So now let's come and talk about my initial premise. Now the iterative metamodeling implementation in this setting. So this is what we said we're going to do. We're going to get our initial points, we're going to train, we're going to evaluate our model, then we're going to train our meta model, and then we're going to use that meta model to go and estimate this Pareto front. And then we can, sort of for validation, we could, if we had the actual Pareto front, we can come and compare them and see how good of a job are we doing. Now, the question that naturally arises, so what should we do? Should we, build a very accurate, meta model, something that can predict a pretty good, global accuracy of over your entire design domain, because then you guaranteed that your, what I call here as predictive Pareto front is going to be close to the actual Pareto front? Or can we be greedy? Can we come and efficiently converge to the correct solution using an inaccurate meta model? We're going to try to do this with this iterative implementation, rather than trying in a single iteration build a very good meta model and then rely on it for our optimization. We're going to come and say, if we can accept some inaccuracies in our meta model, and then still that be able to drive us to the correct solution. Okay, so, and how we're going to do this? So we're going to do this in iterative steps. So after we have our predictive front, we're going to come and check our stopping criteria and see if they're satisfied or not. More on the stopping criteria a little bit later. If they're satisfied, then we're going to terminate. If not, then we go and we say, okay, so we don't have a good enough meta model, we need to improve it. So we're going to go in our design of experiments. We're going to figure out new training points. Then we're going to develop, we're going to evaluate now our response for these new training points. We're going to update our meta model. Then we're going to come and evaluate a new predictive front, and then we're going to go through this whole iterative process up to the point where our stopping criteria are satisfied. So we have talked about all the other subcomponents. Now the two things that we yet need to address, okay, what should our stopping criteria be? And okay, when we try to get new experiments, how we're going to implement this adaptive design of experiments in the context of this design under uncertainty formulation. So for stopping criteria, we're looking at the iteration wise improvement. So in other words, we're going to come and compare what is the new Pareto front to the Pareto front that we had in the previous iteration. If there is a significant discrepancy, evidently we haven't converged, so because the new meta model allow us to identify significantly different Pareto fronts, so we need to move in the next iteration. If on the other hand there is a close proximity between the two Pareto fronts, it means that even further improvements of your meta model is not really allow you to come and do a much better job. So then the question is how to define this discrepancy or closeness between our solutions, and how we're going to do this. We're going to, and especially we're going to try and do this incorporating explicitly the uncertainty that comes from the meta model prediction error. So we define this probability of superiority, which is the probability that one a design configuration is better than another design configuration, and where the probability here we're estimating, incorporating explicitly the meta model uncertainty. If this probability is far from 50%, it means that at least one of the two designs clearly outperforms the others. If it's close to 50%, it means that really our meta model cannot distinguish which one is the better one. So as a definition of closeness, then we're looking at, okay, what is the departure of this probability of superiority with the ideal of 50%. I call that ideal because if it's 50%, it means that pretty much the two designs that you're comparing are completely indistinguishable. So this is now the formal definition of this probability of superiority is a two-dimensional, pretty much integral over conditional realization of your performance objectives for the two design configuration that you're examining. So how do you get this conditional realization? So in reality, this is the information that you have for your Gaussian process. Metamodel, you mean the predictive mean and the predictive covariance for looking at the different x and theta regional design domains. So I'm going to come and demonstrate this through for a two-dimensional implementation, 1x, 1 theta. Sort of, you can come and now get samples from this distribution. Now this is how one of the samples would look like, and in reality getting this sample is fairly straightforward. So this is a Gaussian process. You can start relying on getting a standard Gaussian variables, and then transforming to get the conditional realization of your response. And then pretty much you're looking at a projection of that response to your different design configurations that you are comparing, and we're looking at projection because ultimately, this guy corresponds to integral with respect to theta. So pretty much you need to come and evaluate over all the different, possible thetas, and again, stochastic, simulation is since we cannot get an analytical solution. So here we will evaluate, what is the difference of our conditional realization of our predictions for the objective function for the two different design configurations, and then you repeat this for different samples or for different realization of your Gaussian process. And after you have many samples, you can come now and get your sample-based estimation of your probability of dominance. So, and this pretty much we're gonna use this as a measure of closeness. And in order to have convergence, you need the current Pareto set to have stayed close enough to at least one of the precedent members. It doesn't require that that this Pareto point is close to all the members of the previous set, but it needs to be at least close to one of the precedent ones. So this gives the birth to this convergence indicator, which pretty much, to consider both objectives, you're calculating the maximum discrepancy in either, of the direction of the objective space, and then you figure out, okay, when I compare what is my closest the closest member of the previous Pareto set. So in other words, you come and compare here each of the new points to all the precedent ones, and then you figure out what is the minimum distance. And looking at the global now, so this is convergence for each of the different new Pareto points. For global convergence, you go and evaluate, okay, what is the maximum value over all over all the different Pareto points. If this is not smaller than a threshold that you've set, it means that you haven't converged, or at least in some parts of the Pareto set you haven't converged, so that you should proceed in the next iteration. So when you proceed in the next iteration, the first thing that you need to do is you need to generate new experiments, and we're going to do this through a sample-based approach. I'm going to quickly remind you of the steps. Generate candidate samples based on some preference density. Based on your utility metric, figure out what kind of those samples you should use, and then come and cluster those retained candidate samples to the desired number of new experiments. And the only tricky thing here is specifically, okay, what's going to be the preference density? And in all reality, you need to come and separately define this density for your design variables or your uncertain model parameters, because you have fundamental different requirements of the accuracy of the new meta model with respect to those two components. So let's come and talk a little bit about this. For the design variables, you generally thinking that, okay, the current Pareto set is a good approximation of the domains of interest, because you think that you're going to converge in those locations. You're not caring of improving the accuracy in subdomains that are far away from the set that you currently are identifying. So you can pretty much do a KD, kernel density approximation, and you can see, okay, these are the domains, this is my new preference function, these are the domains that I want to put more experiments. But of course, do you need to consider all the Pareto points? Not if you have converged for some of them. And generally, you can come and try to evaluate convergence looking at the closeness in the design space, but it's much better if you come and do it in the objective function space, because that sort of automatically takes care of sensitivity information. So now we can come and leverage our previous definition of what closeness is, like using the probability of dominance, and generally we can come and exclude points where we think that the Pareto set has already converged. So rather than using all these points to define our DoE for the design variables, we're going to come and exclude the set of convergent points. So rather than having this preference function, we're coming and sort of focusing on parts of the Pareto set that we don't think yet we have converged. So this gives you like in this kernel-based approximation gives you the preference function for the DOE for X. For theta, pretty much this is a little bit easier. So we really are caring for domains where correspond to higher values of the integrand. This is a very similar concept as we do at importance sampling. So pretty much your preference function should be your importance sampling density. And here we do a sample. We do an approximation where we average over all the different objectives. So ultimately, this gives us the preference density of the augmented space, where the theta component corresponds to the importance sampling density for your integrand, and the X component corresponds to domains that are close to our current Pareto set that we don't think yet has converged. In terms of utility metric, so sort of here we're going to use directly what is the variance of our performance measure. This is simply Taylor series, first of the Taylor series expansion, where we propagate the error, the prediction error from the response to the performance. And with all these components, now we know what our DOE is, and we can come and implement it. And as an example, let's come and look at the implementation of these ideas in the design of a half-car nonlinear suspension system. We are modeling the road as a stochastic process with an isospectral characterization. Overall, our model includes 15 uncertain variables. Pretty much every component of our model is treated as uncertain. Again, you can see here the schematic of the half-car model. And our design variables are pretty much the characteristics of a bilinear passive suspension damper. Now, in terms of our two performance objectives, the first one corresponds to the passenger comfort given by the probability that the RMS acceleration will not exceed some acceptable threshold, and we adopting here a log normal fragility to quantify that reliability. And the second objective is what is your road holding of your car, and this is going to be the average RMS force for the front and the rear tire. These are pretty common objectives that we use for design of car suspension examples. And remember that we have, this is our initial objectives, and we're going to come and modify them, incorporating explicitly the prediction error of our meta model. And this is how this, modification looks like. So sort of for your objective one, you come and have now an increased variance in the denominator, where this is the component that comes from the variance of your predictive error. So this is how you explicitly incorporate and propagate the uncertainty from the meta model into your modified performance objective. For the road holding, because pretty much you have the expected value of this guy of your response, the prediction error, because it's zero mean, it doesn't show up. And of course, if you want the gradients, I would say we can explicitly leverage gradients. This is how they're gonna look like, where again, you can come and explicitly get the gradients of the components that come from your meta model. So we can come and implement our multi-objective design under our uncertainty computational framework. And this is sort of the Pareto front that we get in the first iteration. Then we can train a new meta model. This is sort of the updated Pareto front, not because we solved the problem again, but simply because we now have a better model. So pretty much we're going to evaluate exactly for the same Pareto set, but with a higher accuracy meta model. This comes and shifts a little bit the Pareto front. But of course, now starting, we can re-optimize, and pretty much now we can come and get a modification of the Pareto front, and we can gradually then move in the second iteration, third iteration, and you can see that up to some point in the fifth iteration here, you can come and converge. This is what when the performance is evaluated by the meta model, so sort of this is what the optimization approach thinks that performance is, because it relies on the meta model, but you can see if you sort of go and evaluate it using the actual numerical model, you can still see that you have this strong convergence characteristics across the iteration. So it's not just what the meta model thinks it's doing with respect to the actual model. You still see that you can, converge into a final solution. And here we can compare our solutions to a reference solution that we required quite a significant computational burden in order to get. And you can see like a significant smaller computational burden when you use this iterative meta model development. But in terms of the quality of the solutions, you can see that pretty much the Pareto sets match pretty well. And so that we validate that this is not just a glitch for a single implementation. We went and implemented it 5 different times, and you can see like in all the different trials you have very good convergence, high accuracy convergence to the reference solution. Here we added the 500 points per a new iteration. Here we added 200 points per new iteration. You can see that in here, of course, overall you have a significant smaller computational burden. Only you have some challenges in the subdomains where it correspond to rare event, at least for one of your performance objectives. So you have to be careful of how exactly you're going to select what's going to be the number of training points per iteration. And here we come and compare with another algorithm that has been, specifically designed for computationally expensive multi-objective problems, Sokemo. So you can see that, like Sokemo does good in some regions of the Pareto front, but pretty bad in some other regions, and that with significantly higher computational burden corresponding to this, iterative implementation. So, in general, being able, especially focusing on this simultaneous meta model development for both uncertainty, uncertainty propagation, and then design optimization, and then, carefully designing our iterative approach, we can see that you can, leveraging in some stages an inaccurate meta model, you can convert to the actual Pareto front, and you can do that with significant smaller computational burden when you compare to other alternatives. So for the end of the talk, we're going to spend a few minutes looking now for a different UQ task very quickly. So the same concept of iterative meta model implementation for stochastic sampling. So this is our setting, and I'm not going to have design variables anymore, so you're only going to see thetas. But what I'm trying to do in terms of stochastic sampling is generate now samples from a target probability density that is proportional to your prior information, but also proportional to your system function. So you can have a setting like this when you're looking at importance sampling, or subset simulation for rare event estimation, or posterior Bayesian analysis. And generally, for this problem, which is again simulate from a target distribution, when that involves the response of a system that's evaluated under complex numerical model. So the different approaches exist for this stochastic sample. You can do rejection sampling, Markov chain Monte Carlo, but all of these use samples or trials from some proposal density, try to approximate the target density. And in general, their efficiency is evaluated by the number of trials needed in order to obtain one equivalent independent sample. And generally, the higher efficiency you're going to obtain, the more your proposal density comes and approximates your target PDF. Of course, this is typically non-trivial task, especially for high-dimensional applications, for peak posteriors, or for rare events. And many times we do this in a sequential implementation. So this is your initial prior distribution, and this is sort of your target, your posterior. Rather than trying to jump in one step from your prior to your target, you use a series of intermediate densities where the difference per stage is smaller, so you can use this as a proposal density to get samples from here. So through these intermediate steps, you try to not jump as much per iteration with a hope that, again, this is going to be a good proposal density for the next step. But of course, at the end, you really care about simulating samples from your target. So sort of these intermediate steps are there to help you get to that target. Okay. So again, this is this is a similar setting both in terms of base and updating, for example, for transitive MCMC, but also when you're looking at things like subset simulation or cross entropy in important sampling. So okay, let's now try to infuse this iterative metamodel development for our stochastic sample. Pretty much it's straightforward. We're going to come and substitute our exact model with our surrogate model. So we're going to have the approximated target PDF. Now the question is, okay, so how should we do this? Should we develop a metamodel per state, especially in the context of the sequential sampling? So in other words, a separate metamodel to jump within its subdomains. This could be a good idea, but what we're going to try here, we're going to try it with a single metamodel again, cover the whole intermediate steps so that we go to the target density rather than doing a separate metamodel per stage. Because we think this is going to give us a better accuracy. So, and again, how the iterative implementation is going to work, we're going to get some initial experiments, we develop our Gaussian processes, then we're going to see, use stochastic sampling to simulate samples from a target approximate density. And generally we have here preference for rejection sampling for a couple of reasons, because it gives you independent samples, and also because we can exploit the metamodel capability for providing vectorized predictions. If you were doing something like MCMC, because you have dependency between the samples in a Markov chain, you cannot leverage efficiently these vectorized predictions, unless you try to rely on independent chains that you're going to simultaneously propagate. But again, because we can do a lot of estimations using our metamodel, we don't have significant computational burden. Rejection sampling, even though it has, you require a lot of trials to get one independent samples, because you don't pay any significant computational cost for those trials, it ends up being very efficient in this setting. So the iterative implementation, after we get some samples, we're going to check our stopping criteria are satisfied. If not, we're going to proceed to the next iterations, where we're going to again get new experiments, refine our meta model, and continue this iterative step. If the stopping criteria are satisfied, then we stop. And at this point, you have samples from your approximate density. If that's good enough for you, you're okay. But if you really want samples not from your approximate density, but your exact density, in other words, you don't want to rely on your meta model, we still think that these two are similar to one another. So you can do one final stochastic sampling stage by using this as a proposal density to get samples for from your actual target density. In this case, you're not going to rely at all at your metamodel. Now, what are our stopping criteria? Again, since we're doing an iterative step, we can come and compare what is the approximated target PDF at the current iteration with what was the approximated target PDF in the previous iteration. Since we're approximating PDFs, we need a measure that's going to compare PDFs, and we're going to use here the Hellinger distance. Again, this is the expression of the Hellinger distance when you compare these two PDFs, and we're going to do a sample-based evaluation. Again, you're going to rely on the meta model. It's very computational efficient to do this approximation. So if the Hellinger distance is high, significantly greater than 0, it means that those two densities are not close enough. So refining the meta model has really come up and gave you really different samples than what you previously had. So you should, it's a good idea to go and to repeat the process into the next iteration. In terms of design of experiments for refinement of the metamodel. We're going to do here a dual approach where we're going to combine a target-based DoE. Again, it's always going to be a sample-based DoE. The preference function is going to be your target density, and your utility metric is, again, is going to be this predictive variance for your system function. This is exactly mirroring what we do before. But, and note here that I really am focusing on my final stage of my sequential sampling. The question is, okay, I do understand that ultimately that's my end goal, that's my UQ task, but remember that you do come and use your intermediate densities that help you reach your final one. So you still don't want to get lost in the intermediate steps as you try to converge into your final target density. So, and again, this target-based DoE doesn't take care of the intermediate path. So we have another part of our DoE strategy is what we call response-based DoE, and this sort of comes and uses preferred functions, the intermediate densities, and as utility metrics, the differential entropy between our prior or posterior response predictions. So pretty much here we're coming, for each candidate point, we come and say, okay, how much information have we extracted for that point based on our existing experiments? And if that information is not high enough, we say, okay, probably we could do a better job. So this is a good candidate experiment to go and obtain more information. So at the end of the day, we come and compare, we come and combine for our DoE both this target-based and our response-based DoE to end up with a hybrid design of experiment approach. We're going to come and demonstrate it very quickly in the context of rare event estimation using importance sampling. So in other words, this is sort of reliability estimation. Your performance function is just the indicator, function. In this case, your target density is the integrand, or the probability density for your theta conditional on a system failure. And in terms of now, after you converge to your target approximate density, ultimately our goal is to come and estimate this probability of failure. You can either, completely rely on your Gaussian process, so in other words, not only you used your metamodel to approximate your target density, but also you use your metamodel in your importance sampling estimation of your probability of failure, or you can come and incorporate, I'm not going to come and use my response function that comes from the metamodel. We're going to come and use an actual, the exact response function. This is sort of what we are suggesting, because at the end of the day, this removes any biasness that you can have in your final results stemming from the metamodel. Very quickly, two examples. One is going to be a simple trust example with 10 variables, and the second is the optimization, the design of a floor isolation system. In this case, you have a little bit higher dimensions, so 36 variables. So here you can see and actually we have two, as you have pointed out, we have two versions of the trust example. One when you are looking just the response in the middle, and then we'll come and look at the response of different parts within the trust for coming and defining what acceptable, what failure is, what acceptable performance is. You can see here on the three different examples how across the iterations of our implementations, the Hellinger distance between the approximate the target PDF really comes and reduces. So you can see that at some point it reaches a plateau. This is evident that even if you came and used more experiments and you try to further refine your meta model, you wouldn't be able to get significant, improvements. And here, this is sort of the Hellinger distance between the approximated target PDFs. This is where we come and compare between the approximate target PDF and the actual target PDF. And you can see that this measure here is a good indicator of how well we're doing with respect to the actual PDF approximation. Now looking at, okay, now after I approximate the PDF, how can you use it within the importance sampling setting? So you can see here what would be the probability of failure if I stopped at this iteration and then I relied completely on my Gaussian process to approximate it. And you can see that very quickly you have some significant convergence, and at some point pretty much you get completely unbiased results. But of course what we are suggesting is, don't come and rely on your Gaussian process for estimating the probability of failure. Just rely on the Gaussian process and the approximation of the target density to inform your importance sampling densities. In that case, okay, since I'm only using in terms of importance sampling, how good that target, what are the benefits from that, iterative implementation. So pretty much this comes and evaluates what is the number of samples that we need in order to get, I think, coefficient of variation of 5% of our stochastic simulation if we, for example, had stopped at the second iteration and we used that approximation of a target density as important sampling. You can see that again very quickly. You come and then you reach a plateau. Further increasing the iterative implementation, further refining your meta model really doesn't come and give you any significant advances. And this is sort of an overall comparison for the two examples. We come and compare with other existing approaches, and you can see that the suggested implementation, which we call AKSSD in general, it gives you significant computational efficiency, and even if it gets beaten by some of the other approaches, you can see that it gives you more unbiased results. Of course, if you're talking about an event of 10 to the minus 5, coming and comparing if it's 3.5 and 3.2, it doesn't make that much sense. So, these are the conclusions. In this talk, we talk about, iterative implementation of surrogate modeling, and we saw that it can facilitate significant computational benefits for UQ application. And Gaussian process metamodels are especially relevant due to the holistic treatment of the uncertainty that comes from the metamodel predictions. It's very important to adaptively control the metamodel accuracy with a goal to convert to accurate solutions, leveraging perhaps inaccurate meta models, and especially we can do this within an iterative implementation. Especially for design and uncertainty development, the meta models in augmented input space can facilitate significant computational benefits, sort of because with a single meta model, you address both the uncertainty propagation and the design optimization. And finally, for design of experiments, generally it's a very difficult task. The sample-based DoE, even though it's not going to give you the actually optimal next experiment, it's very efficient and it still identifies experiments that can facilitate significant accuracy improvements. Maybe not the optimal accuracy, but significant benefits. And I would like, generally you're always as good as your students are, so most of this work has been done by Zize Zhang with some of the initial results by Juan Camilo Medina. And with that, thank you very much for your attention.